Welcome to Linear Algebra. This video is lesson 1 of this course in Advanced Mathematics, and linear algebra is typically taken after the array of calculus courses, although calculus is typically more difficult than linear algebra in the actual implementation, but linear algebra can be more difficult in terms of the conceptualization of the different components of it and the usage of it. But it basically is an advanced math that ties together all forms of mathematics that come before it. This is the primer by which we use all other math in the sciences, in STEM, science, technology, engineering, and math. Linear algebra is used in computer programming, engineering. It is vital. Without linear algebra, we are not able to do things like put a man on the moon. It is that vital as the concepts of calculus, which measure change. Linear algebra is basically how we work with very large amounts of information and coding it on a level that we can use it. So what does linear algebra mean? Linear algebra is actually an algebra course that works only with linear equations of the form ax plus b equals y. So with that form, you are then able to use the variables in the equations to plug in numbers and get the exact same information per equation. In other words, the equations come out in a consistent way when you fill in a number for each variable. Like say you have the variable x. If you say x equals 4, for each equation, x will equal 4 if the equations are consistent. And this is very important because you need these equations to work. They need to work in relation to each other. Their relationship with each other is the key component that enables linear algebra to work in things like computing. Okay, so in linear algebra, what we use is called the matrix. This is the way we express linear equations in a simpler form. A matrix is a simple way of writing the form of a system of equations, linear equations, that is. Now, we are all familiar by this point, studying linear algebra, with the basic algebra of linear equations. So you have a system of equations, 1x or x plus 2y, and 3x plus 4y. That is a system of equations. What that means is that they include variables, and when you plug in a number for one of the variables and the other variable, like you say x equals 4, y equals 2, something like that, these equations will work. And that's what that means. But for the time being, we are not having an equal sign. These are called coefficient equations. So basically it just has the numbers with the variables and not the equals. But we are all familiar with this form of system of equations and how to solve for x and y. We will get into that later, but for now we want to know how we write this system of equations as a matrix. What is a matrix? Okay. So you take the system of equations and you form a bracket around the numbers only. The point of the matrix is to eliminate the variables altogether, so you are working only with the basic numbers, and you can do your calculations with respect to the relationship of the numbers to each other. So thereby, you're making it much simpler. You're getting rid of x, y, any other variables you have, anything that's there that's not the number, the basic number, the coefficient. So the matrix is just taking these numbers. Here's the 1 will go there, the 2 goes in the same position, the next one, 3 and 4. What this means is this is equation 1. So equation 1 will go into row 1. Row 1 is across, horizontal. Equation 2 will go into row 2. Row 2 is also horizontal. And the vertical, you will notice the columns. These are columns. These are the same numbers with respect to their positioning. Upper left, upper right, lower left, lower right. So by column, you are isolating variables. So this is the x column right here. These are the x variables, and this is the y column right here. And that's just very simple. That's how you write a matrix. That's how you form a matrix. And then when you do your calculations, you take up a lot of less time and space and thought, and you just focus on the relationship of the numbers to each other. And that is the whole point of linear algebra. So, the matrix. What are matrices? It's not the movie with Keanu Reeves, although that is as complicated as matrix mathematics, as we call it, can get. It can get that complicated. Matrices are concise methods of expressing algebraic expressions or equations, as we just discussed, and they must be linear equations in the course of linear algebra. It is important to know in matrix mathematics that rows mentioned first are horizontally placed, as we just mentioned, and columns are vertically placed. So here's the first row, 2 and 3, and that is how we write it. The second row contains 4 and 1, and that is how we write that. Now column 1 contains 2 and 4, and column 2 contains 3 and 1, and that is how you write these. Now what is important is that this matrix is congruent to this system of equations down here. 2x plus 3y, here's the 2 and the 3, in the same positioning, and the 4x plus y, 4 and 1 for y. This is the matrix form of this system of equations. Now, this is a coefficient matrix right here because it does not have an equal sign. It simply deals with the numbers that are in front of variables, and that is the coefficient matrix up here. The coefficient set of equations yields this coefficient matrix. Now, this can also be an augmented matrix, which means that it equals something which does not contain a variable and thereby enables you to solve and determine whether it is consistent or inconsistent. So you can say, okay, this matrix would be 2x equals 3. So pretend that there's an equal sign between the set of numbers here. So 2x equals 3, 4x equals 1. And that would be the augmented form. So instead of this just being equations, it would then have you would put a dotted line here and it would indicate an equal sign. So there are two forms of that. So you must determine in each problem, you must specify whether it is a coefficient or augmented matrix. Otherwise, the math that you perform, the mathematical operations that you perform on it will not come out correct. So that is a very important thing to know, whether they're complete equations or whether they are just sets of relationships as over here. Okay, so one important thing to learn first, beyond understanding matrices, is how we add them together. So these are very basic initial principles to learn. the addition of matrices will look something like this. You have these two matrices. Here's one, and here's another one. So this one plus this one equals what? How do we do that? It is the same with subtraction. Follows the same formula, replacing the plus with a minus. But what is that formula? Okay, referring back to addition, each number's position in the first matrix coincides with the same position in the second matrix. Therefore, to add the matrices, simply add the coinciding terms. Hence, this is upper left, and so is this. So you would add the 1 plus the 2 and yield a number. 1 plus 2, upper left of the first one, which is 1, plus the upper left of the second one, which is 2, equals 1 plus 2 equals 3. So 1 plus 2 equals 3. Upper right of the first one, which is 2, plus upper right of the second one, which is 3, would yield 2 plus 3 equals 5. 2 plus 3 equals 5, and you position the answer as such. You do not have to write this out if you can do it all in your head. This is just to keep you from getting confused, because you have to, in linear algebra, it's very easy to get misaligned or confused, to lose your place, to forget what you did already. So in the beginning, when you're first learning, it's good to write it out so everything is organized and it makes sense. Okay, so lower left, the lower left of this one is 3. The first one is 3. Lower left of the second one is 4. So 3 plus 4 equals 7. And the lower right of the first is 4, plus the lower right of the second is 5. 4 plus 5 equals 9. Very simple, right? You just do it by the positioning. Now, what is an important thing that you notice about these matrices? It should be very obvious. They are the same size and shape. They have to have the same size and shape. It means here's a row, here's a row, here's a row, here's a row, here's a row. Here's a column, 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 column. Now, these rows and columns have to have the same number of numbers in each for each of the matrices. You can have a different number of columns with respect to rows in the matrices themselves, but in terms of the two matrices, they must be identical in size. Therefore, if you have 2 rows in this one, in the first one, you have to have 2 rows in the second one. That's the first rule. If you have 2 columns in the first one, you have to have 2 columns in the second one. So those are very specific rules, unbreakable. By virtue of this, like as another example, if you have 2 rows and 3 columns in the first matrix, you must have 2 rows and 3 columns in the second matrix. They must be identical size and shape in order to add or subtract them. And again, when you're subtracting, all you're doing is changing this to a minus sign, and it would be 1 minus 2. So you would get -1 in the first position instead of 3. So it's very simple. You just have to keep it straight, like what exactly you're working on. You have to keep track of each position, and you have to do item by item, basically term by term, to do the mathematics on them. And it's very simple. This is beginning linear algebra. Okay, now this is more complicated. The multiplication of matrices has no relationship to addition or subtraction. And you can only do addition, subtraction, multiplication. You do not do division on matrices. That is an explanation that we will learn later, but you will be thankful that you don't have to do it. Trust me. Okay, multiplication of matrices. So, if you then have these same matrices, you will recognize them from the last example. However, we are now not adding them, we are we are multiplying them. We are multiplying these two matrices together, and you don't even need to put the X. I just put it to overemphasize. Often they will just be sitting next to each other the way you would do with numbers, and you would put parentheses instead of like, multiplication sign. But you have to put some indicator. You can just put them next to each other if they're matrices, because it's understood that these are multiplied. Okay, so to find the shape and size of the answer, which is your first issue, and this actually is a bad example because I end up with the same size and shape as both of the previous matrices, both of the matrices that I'm multiplying together. So it's not a prime example. I will do another example, but for now, I'm going to try to explain this in a way that makes sense. So before you do any computations, don't even do anything. Take these two matrices and say, okay, what are they multiplied to become? So how do you do this? Take the first one and put it here, just recopy it like that. Take the second one and put it kitty corner. Matrices can be multiplied only if the number of columns in the first matches the number of rows in the second, as you will soon see. But to find the shape and size of the answer matrix, place the two matrices kitty corner, as I have done here, on a diagonal point to point, such that the answer matrix height matches the number of rows in the first. Notice that there's two rows in the first one. Here's the first one, here's the first one, row 1, row 2. So this has to have the same number of rows as that first one. And its width matches the number of columns in the second. So the answer matrix matches the number of columns. This is the second matrix. Here's the second matrix. It has two columns, so this must have two columns. So the number of rows here is the height of the answer. The number of rows in the first matrix is the height of the answer. The number of columns in the second matrix is the width of the answer. This is very important. And as you will notice, a huge difference between simple numbers and matrices. What happens when you multiply 2 times 3? It equals 6. 3 times 2 also equals 6. So you can change the order. They are interchangeable. They're commutable. It is not true with matrices. You cannot switch the order of these two matrices and come out with the same answer. Matrix mathematics does not work that way because of this rule of how you multiply them together. Because of what I just said, the rows of the first match the height of the answer. The columns of the second match the width. So if you were to have different size matrices or whatever you have, just switching the order, the outcome becomes different because you're following rows of the first and columns of the second. I'll explain as we're doing. We're just going to do the computations. So the matrices can be multiplied only if the numbers of columns in the first one. So now we're talking about the columns in the first one. It has two columns. Matches the number of rows in the second. Okay, so we're looking at these two matrices. This one, the first one has two columns. The second one has two rows. Why do we care about that? Who cares? What is all this row column stuff? Okay, you will see in a second why this is important. Now this is very strange. Pay attention to what I'm doing here. When you multiply these, it is not item by item in terms of upper left, upper right, lower left, lower right. There's not a direct correlation. It is done as such. multiply the matrices by multiplying each term of a row, horizontal, of the first one by each coinciding term of a column, vertical, of the second, and adding according to a row by column multiplication. Thus, position by position, you multiply the terms. In row 1, which consists in matrix 1 of 1 and 2, times column 1, 2 and 4 of the second matrix. I'll explain this a little bit better. Okay, so here are the rows of the first matrix, and here are the columns of the second. So what you do is you take this first item, first position, so you're dealing with rows here, and you're dealing with columns here. 1 times 2, so the first two items. But then, what do? So 1 times 2, you get that answer. You write it down. You move on. You move to the second item in this row of the first one. 2 times, now what? What is it times? It's times 4. Because as you're moving across the rows of the first one, you move down the corresponding column of the second one. That's how you do matrix multiplication. So, row 1 would be 1 and 2, 1 times 2 plus 2 times 4. There's the answer. 1 times 2, 1 times 2, plus 2 times 4. Notice I'm moving across this row as I'm also moving down this corresponding column. So what this yields is you're writing down all of your work. 1 times 2 plus 2 times 4. So then you have 2 plus 8. And the answer is 10 for that first position. They correspond in the end. Excuse me. Okay, so now what do? Bear in mind, this can be done in any order. It doesn't matter where you start. You just start with the first matrix. The trick is to multiply corresponding things together and do in the order that it goes. Okay, so if you were wanting to get this position right here, upper left, you would do across row 1 and down column 1. So that's what we have done, and it yielded 10. So now what do? Now you take this row. So you've done row 1, move to row 2. This is a simple format that makes sure you multiply everything and you get all the positional answers. So we've done row 1 with column 1, so now we're going to move to row 2 with column 1. It's systematic. That's the key word with linear algebra. So what do you have in row 2? Okay, so 3 times 2. First term of row 1 times the first term of column 1. Row 2, sorry. First term of row 2 times the first term of column 1 in the second one. So it would be 3 times 2 plus second terms 4 times 4. You see how this works? On the left, the first matrix, you're doing row only. So you're going horizontal as you go, as you do the computations. In the second matrix, you're doing vertical, moving from item to item. So that is the rule. So it would be 1 times 2 plus 2 times 4. 1 times 2 plus 2 times 4. 2 plus 8 is 10. Then you have 3 times 2 plus 4 times 4. 3 times 2 plus 4 times 4. 6 plus 16 is 22. Okay, so what comes next? Are there any guesses? Well, you did column 1 for both of these rows. So now you do column 2. You just repeat the procedure. So 1 times 3, 1 times 3. Notice what I'm doing here. plus 2 times 5. Notice how I'm moving across and down. I'm shifting it. So, okay, 1 times 3 plus 2 times 5. 3 plus 10 is 13. And notice that that goes in that second position. Okay. So now the next one. What happens next? What have we not done yet? We have 3 answers. What's the fourth? Okay. So 3 times 3, 3 times 3, 9, plus 4 times 5. 4 times 5 is 20. See how this works? 3 times 3 plus 4 times 5. As you move across over here, you move down over here. And you just got to make sure you do every row on this side times every column on this side. So basically, it's component by component, the rows of matrix 1 times the columns of matrix 2. And that is the way you do matrix multiplication. This is actually the more simple form. These are considered to be 2 by 2. Remember how I said that rows and columns, you mentioned rows first and then columns. So therefore you can keep the size of the matrix clear to anyone you're discussing it with. This would be a 2 by 2. Each of these are 2 by 2 and the answer is 2 by 2, which is why I said it's a bad example, because you can have asymmetrical matrices that yield a totally different size answer than either of those matrices, but this one happens to be the same size because it is square, because it is 2 by 2. 2 indicates rows. There's 2 rows in each of these. So that's the 2, that's the first 2. Then there are 2 columns in each of these. So if we're just considering this one matrix, it would be a 2 by 2. 2 rows by 2 columns. And this is the same. And then the answer is the same. But you actually can have 2 different size matrices and multiply them together if the number of columns in the first matrix matches the number of rows in the second. In other words, okay, say for example, you have 3 columns in the first matrix. How many rows do you need to have in the second one? 3. You need to have, and why is this true? Okay, let me just explain it like this. Say you have 3 columns in this instead of 2. Say there's another one here. What happens when you multiply it? You would start with this term that's invisible over here times this one times this one, and this one times, oh, I need another term here. You see how you move across over here and you move down over here? So therefore, if you're doing component by component multiplication, the number of terms in a row in the first one has to have the same number of terms in the column of the second one. So the number of columns in the first matches the rows in the second. That sounds confusing, but if you have these columns, each column is a component of a term in the row. So what you're doing is you're moving across here as you're moving down here. If you go across 1, 2, 1 times 2 plus 2 times 4, that's it. If you have another term, it's x times 2 plus 1 times 4 plus 2 times x over here, something over here. So that's the way that would work. And you just need to have the same number, otherwise you can't multiply anything. You can't, if there's nothing there, you can't multiply it, and then it would yield an incorrect. It's basically undefined. It does not exist. So that's why the number of columns in the first has to match the number of rows in the second, so you can actually perform the multiplication. But just to reiterate this, 1 times 2, 1 times 2, plus 2 times 4, plus 2 times 4, 2 plus 8 is 10, that's the first position. 3 times 2 is 6, plus 4 times 4 is 16. 6 plus 16 is 22. Then this position up here for the answer. 3 times 3 is 9, plus 4 times 5 is 20. I'm sorry, that's the fourth position. I did the second row. 1 times 3 is 3, plus 2 times 5 is 10. You can see how this can get like very confusing, but basically you just have to keep it straight that you're doing component matching to component. You always start upper left and match them. But as you move across here in the first matrix, you're also simultaneously moving down here, and that is the rule with matrix multiplication. So, matrices are the way that we perform linear algebra computations, and these are the expressions of the linear equations as mentioned. And as I mentioned, this would be a coefficient matrix because it has no equals. They're just equations without equals. They're just floating equations relative to each other. Now when you have equal signs in there, it becomes augmented. So this is a coefficient form of a system of equations, and this is an augmented form of a system of equations. But they can be written as the exact same matrix because the numbers are the same. This would be 2, 4, 3, and 1, 2, 4, 3, and 1. Doesn't matter. It's the same matrix because it's the same amount of numbers in the same positions. All you're changing is you're saying the variables x and y. Like this is an x column, this is a y column. But in this case, it would just be an x column and they would be equal to these numbers. These are numbers, not variables. So they would be augmented to those results. And thereby you could actually solve the equations. And we will be doing a lot of solving of equations and calculating matrices and different forms of simple computations that you do under the heading of certain concepts that you need to know in order to determine what comes next and what you're going, how you break computer codes. There's so many things that you can do with linear algebra. But these are the basics to start with. And we covered addition and also subtraction. I could have done an example of that, but it's really not necessary because it's exactly the same format. You just change the plus to minus. And then the multiplication is as such. I need to do an example with different size matrices, but this is what we will start with. And I hope you enjoyed my lesson. I hope that this is starting to make sense. It's actually a lot simpler than you would think, but at the same time, you will see just how complicated linear algebra can become as you go through. So it is very important to grasp the basics and master them, practice them. Do different examples in a linear algebra book. See if you can come out with the answers. The odd number answers should be in the back. And if you don't understand, look in the beginning section and look at the examples and see how they have done it and try to duplicate and practice and become comfortable. Don't get confused. Sometimes you can become dyslexic or lose your place. And I had a lot of that when I was first learning, especially with the matrix multiplication. It made no sense to me. This is so bizarre. It's so different from the way you multiply regular numbers or even in algebra with variables. But because these are sets, they belong together in this matrix. That is the relation. If you're going to do something like that, you have to keep the terms together. And that is the reason that you do it like this. That is the reason that one of them is going one direction and one of them is going another direction. That is the way you work geometrically through them. So, thank you for bearing with me through this lesson 1, and there will be further lessons to come. Thank you.